hear me? Yep. Oh yeah, good. I'm Rasmus Haugaard. I'm working as a research associate with Middle Earth and Merck, and I've been doing that for the last 7 years now, I think. And today I'm gonna give you an update on the Hope Bay work from the Hope Bay camp. Oh yeah, okay, you're recording. Sorry. Today's talk will be a little heavy on the geochronology stuff because we just got bombarded by Mike Hamilton's or a lot of the dates, 8 states and results. So we're gonna try and interpret these results, and I'm gonna show, for those that's MT hungry at the end, we will show some of the MT work from the Hope Bay too. And of course, this is in close collaboration with Agnico Eagle, who runs the Hope Bay camp. So the Slave Craton, so Hope Bay is up here in the northeastern part of the Slave Craton in the Bathurst block, and this is the Slave Craton. And the Slave Craton consists of 30 plus different various greenstone belts distributed throughout. Major part of these greenstone belt is the Yellowknife supergroup composed of the CAM group 2730 to 2700, and then the Banting group volcanics, felsic and intermediate volcanics 2690 to 2660 approximately. And Hope Bay's volcanic rocks will be situated in these CAM group and Banting group volcanic equivalents or volcanic rocks. The Slave Craton, what's so interesting with the Slave Craton is the central and western part of the Slave Craton has very old basement underneath the greenstone belts, but the eastern part right here has no sign of older basement underneath, so that reminds us a little bit of the Abitibi greenstone, or Abitibi belt. Some of these greenstone belts out here in the east. The gold production in the Slave Craton has been not as big as in the Abitibi or in the Superior Craton, a total of 19 million ounces gold produced so far. And there is new mining happening out here in the Back River Gold Project, so there's stuff happening in that sense. I should say that Middle Earth has MSc student, Evan Hall, that's almost finishing his MSc project, I think. He's working in the High Lake area right here, in the ore deposit right here. So if we, just for fun, actually I scaled in Abitibi belt right here, the outline of Abitibi, so you can see that the Slave Craton is not that big a craton. If we zoom into the Hope Bay belt, this is how it looks like. It's bounded by east, west, and south of bounding granitoids, and the greenstone belt strikes south to east most of the volcanic rocks, and the stratigraphy of the volcanic. The stratigraphy is defined by the volcanic rocks. And that's all compiled by Sherlock 2012. The volcanic stratigraphy goes from 2716, the Flake Lakes suite here, to the 2662, which is the youngest felsic volcanic discovered in the Hope Bay. That's the Clover Lake suite right here. And then there's 5 panels of felsic volcanic rocks that's very tight in age range right here. If we go to the major ore deposit in the Hope Bay, the Doris deposit is up here in north, and the Madrid deposit is right here in the central north, and then you have the Boston deposit down in the south here. The belt is approximately 80 kilometers, just to say this. It's 80 kilometers long and 30 kilometers wide. The Doris deposit is the only one that's been mined so far. It has a total of 306,000 ounces of gold produced in 17 to 19. And then the Madrid deposit and Boston deposit is the most important in this talk. So I just wrote down the major gold mineralization style right here under these. I can't even read these, so I can't. The Madrid is the disseminated sulfides in structural controlled D2 alteration zones in iron-rich thorites, whereas the Boston deposits, the gold mineralization is sulfide-bearing quartz carbonate veins. It's hosted, and that's related to an iron-bearing hydrothermal alteration system, iron carbonate, related to a south-plunging antiform. There's a current proven mineral reserves of 3.4 million ounces, according to Agnico Eagle in 2023. Maybe that has changed. So, as I said, I'm going to focus now on some of the work that I and my colleague has been doing around the greenstone belt, because there's a lot that has been done on the volcanic rocks, but hardly nothing has been done on the granitoids that bounce the belts, which is really important to establish the timing and evolution of the Bathurst block granitoids, and also how that relates to the belt itself. So there's two ages that exist right now of the granitoids. That's up here in the northwest and northeast. 2608 million year, and then a 2672 million year age up here. So we've been collecting some samples of the granitoids along the edge of the belt here, and I showed the photos here of the various granites, and they are labeled A, B here, so that relates to these two, and then C, D, E, F, G is over here. So I'm going to show the ages of these in a minute. I will say I have a bonus granite gneiss sample. So I'm going to show you the results of that. That's actually a synolith in a mafic dike. I'm also going to show that the result of that a little bit later. So the western flank of the belt, A and B, is pretty spot on with the age that already existed up here in the northwest. 2609, 2610, so around 2610. This granitoid here is either intruded into the belt or tectonized. The contact here is tectonized. I don't know that, but maybe Ross can add to that story. So these are nice, accurate ages. So if we go to the southeast here, the C, that's a granite gneiss suite, southeast flank of Hope Bay. That gives us actually a little more scatter of data along the Concordia, but the 2649 is presumably the protolith age of this granite. The 2620 is zircons that's been intensively altered and could correspond to a migmatization event in this area, but we are still discussing that. If we go up the flank of the east here, D and E is up here, graphs here. They are 2686 and 2685. So that correlates well with the Windy Lake felsic suite. And if we go up to the F and G here, these are 2680, so a little younger than the D and E. So these ages are very interesting from an evolution perspective. So Mike actually made this diagram and sent it to me the last week or so. And what you see here is a composite uranium lead age for the Hope Bay belt. It compiles all the Sherlock data that in his paper 2012. This is what you see here, the circle spots here. That's the felsic volcanic rocks, and then we added, or Mike added the bounding granitoids into this diagram. And what we see here is the 2686, which is the southern part of the eastern flank of the Hope Bay, is very equivalent to the Windy Lake felsic volcanic. So in terms of the age date, these are probably the first evidence of the synvolcanic plutons to the Windy Lake felsic volcanics. As we go north on that flank, we go south to north. It seems to young, the granitoids young upwards. So we have a 2681 here in the central eastern flank. Nothing seems to correlate with that. There's no extrusives equivalent to these plutons. The Koinok felsicoid is a little younger than these plutons. And then the 2672H up in the northeastern part is obviously a bit younger, but doesn't correlate with any felsic volcanic unit either. So, and then if we go, this is down to the southeast of the belt. We have the 2649 here, and then we might have a magmatization event, 2620. That's actually close to the Boston deposit, and we're still working on how to figure out what this age is. And then no-brainer on the western flank, I would say, with these later intrusion, likely intrusion phase into the belt. As I said, I had a bonus xenolith outcrop here. Mike, you haven't seen this, so I'm going to show you some laser results. That's actually very good from our laser at Laurentian. The sample site is right here in the northern part of the belt. It's taken within a mafic dike that carries these granite gneiss xenolith. You can see them here. Here's some zircons from that sample. And we analyzed 54 or something zircons, and they are all spot on with 2708 million year age. So however you plot it, it's hard to argue that these are not of Flake Lake Suite, the oldest volcanic event in the belt. So this granite gneiss might be or is a synvolcanic intrusion to the Flake Lake Suite. So it's a little bit mystery what that does all the way up north there, but we're working on that. So the MT grid, as I promised, we work on the MT grid over the Hope Bay belt. I showed a lot of that last time, but I'm going to show you some just some very general cross sections here. The great thing about having the MT grid is that you can slice this in any other direction you want, southeast, south, north, east, west. So you can view the crustal conductivity in many angles. So that's great. So if we go from south, crossing the Boston deposit right here, and up to the north, crossing the Madrid. This is the slice that we see, we look right into here when we're looking west. And notable, the Madrid, there's a conductor there. The Madrid anomaly, I call it. It's very restricted. It's surrounded by resistive crust. And it's not connected to this larger C1 conductor down in depth here. So that's kind of interesting, especially when we go down to the Boston area. We're starting to interpret these spider lake anomalies here that goes up to the area just north of the Boston deposit, which is pretty interesting because they connect to the deeper, the C1 anomaly. So if we just slice east-west slices across the Madrid deposit area, this is what we see. This is actually the Madrid anomaly right here, just looking towards north here. And not much volume to it. It's also restricted on both sides by resistive crust. It's not connected to the C1 here either on this angle. And same with the B feature right here. So but volume-wise, the conductive pattern is not so big, and it's not connected to the C1 here. So if we go instead to the Boston deposit area, it's very interesting in terms of the C1 anomaly. These are the east-west slices here. What you will see is the first slice up here is just where the spider lake anomaly starts. It's the C1 anomaly that goes up close to the surface, and it remains there actually on these 3 slices as we go south down the spider lake right here. And then at this one, just 5 kilometers north of Boston, Boston is right here, it actually gets most pronounced, the conductor, the C1 connector that goes up to the surface right here. And then at Boston itself, it seems to be more resistive in this area. So there's some interpretation there to be made. The C1 conductor is really interesting, and if we go, this one shows a horizontal depth slice in 25 kilometers or something approximately. And this is how the C1 connector lines up down in the lower crust. So it actually doesn't follow the greenstone belt. It goes with an angle to it. And if we slice that conductor right here, this is what we see. And it's a very pronounced feature down in the, again, it starts to be conductive in the 15 kilometers range or something, 10 to 15 kilometers. So from a tectonically and geological perspective, we're trying to interpret this as good as we can, and I don't have any final answers to you right now on that feature. We might be able to interpret this in a more larger scale framework of the area up there. So just some thoughts of what I've shown now is that I think we found the first evidence of the syn volcanic intrusion to the Windy Lake suite, which is good. The plutonic, are they the plutonic arc routes to the Windy Felsic volcanics? What is the crustal significance of the 2708 million year syn volcanic intrusive synolith that we found in a mafic dike? That's very interesting. And then, of course, all the issues with the C1 conductor and the relation between C1 and the Spider Lake anomalies, and these Spider Lake MT anomalies, could that be a sign of the, could they be genetically linked to the hydrothermal alteration system that we see in the Boston antiform? Yeah, so lots to do, and thanks, Mike, for bombarding me with all this stuff, so that's good. Yeah, thanks.